All right, and it is 4 o'clock where I am, so I think we should get started. So hello, welcome everyone. It's great to see many people here on Zoom and other people watching through other channels for this session on our Open Energy Benchmark. My name is Harry van der Weijde. I'm Head of Research and Market Development at Open Energy Transition. If you haven't heard about us, we're a non-profit trying to make open source energy modeling mainstream by developing software based on open source tools such as PIPESA, by applying them with system operators, regulators, and other parties, and by delivering training and capacity building. In this specific discussion, we are looking at solvers, because if we want energy modeling to be truly open source, if we want a full open source stack to exist, then of course we also have to look at solvers. Energy models typically need solvers to do anything. So it's not good enough to just have an open source energy model like PIPESA. We also need to look at open source solvers. And we've been doing that over the past couple of months, over the past year, with our benchmark project, which we're going to tell you more about. Just a few housekeeping things. If you are not speaking, please keep your microphone off and your camera off as well. We are recording this meeting. So if you don't want to be in the recording, then don't turn your camera on at all. Otherwise, I'll have to cut you out later. If you have questions to the speakers, please use the chat. It's at the bottom of your screen in this speech bubble icon. So use the chat. Feel free to use the chat to ask questions during the talks as well. But especially at the end, we have a panel discussion where a number of people are going to be answering your questions. So throughout, also already think of questions that you want to ask the panel so that we can have an interesting discussion afterwards. So what we're going to do in this hour is we will first have a keynote speech. And we're very happy to have Julian Hall here from the University of Edinburgh, who's led the work on HICE, the most high-performance open source linear solver. After that, we will have a presentation of our benchmark results for this year, which my colleague Enrico will do. And after that, we'll have the panel discussion. We'll try to stick to time. So I'm also asking the speakers if you could please stick to your allocated times. If you don't, I will turn my camera on when you have 1 minute left, so that you have a signal that it's a good time to move on. So I think without further ado, Julian, over to you.
Thank you. Bear with me. I have a I had an issue with PDFs on my laptop which are generated elsewhere. But anyway, so I don't have my cover page. One thing that Enrico wanted me to comment on was why you need optimization solvers, which is puts me out on a limb. And so this is my understanding of why you need it in energy system modeling. And if basically, if you're doing short-term modeling, you really only need equation solving, and that will mean nonlinear equations, which are hard in themselves. But for medium-term modeling, you have got optimal operating decisions to be made, and they are typically whether generators are on or off. And then there's continuous decisions like power output from generators. And you get rid of you simplify things by not having the nonlinear power flow, by having DC power flow. And that means we end up with mixed integer linear programming models. In the longer term, the the number of decisions get bigger, and so therefore we have to simplify the models, and the discrete decisions disappear, and you're only making continuous decisions, so your models are typically linear programming. And in fact, it's partly the challenges of solving all of these problems which drives what you guys can actually model. And to get these optimal values, you need the solvers. And MIP, for example, is fundamentally harder mathematically than solving LPs. So therefore, you can't solve MIPs at any scale. And so that's why the linear programming model may be the only thing that can give you information. Looking at the commercial solvers that are around, I should say that obviously I've got a Highs hat to wear, and I'm trying to be as objective as I can about things, and I hope I don't upset anyone. So the oldest is FICO Express, which began in the UK as Dash, and it's now part of FICO, and it's still more than competitive, even if it hasn't appeared in Mittelman benchmarks for a while. The Cplex, which was Bob Bixby's original academic creation, has been sold twice. It's got a massive user presence and reputation, but it's no longer being developed. We have Gurobi, developed by Gu, Rothberg, and Bixby.
Argentina veo muy mal, hay mucha mala.
Sorry. And it's provided the best solvers for the last 10 or 15 years. And then there's Cardinal Operations in China, which is developed by a collection of Stanford graduates and my ex-PhD student, Chi Huang Fu. And their performance on the Mittelman benchmarks when Gurobi was still there was generally better, except on the MIP benchmark, where there's still a gap, but it's possible that they are gradually overtaking the Western software. In open source, I'm now looking at the 4 that are NDOET benchmarks. There's GLPK, which is Russian in origin. It does solve LP and MIP, but its performance is generally poor. It's got a loyal user base, but its development has stagnated for many years. We have CLP and CBC, which were kind of versions of MPSX that John Forrest was allowed to release from IBM, and they're part of CoinOR. And the Simplex and MIP performance is quite good. They're very, very popular, but development has stagnated because essentially John is the one who could really maintain the code base. Zoplex and SCIP were developed at the Zuse Institute. Zoplex solves LP and gives fair performance. SCIP solves MIP and gives good performance. These are very popular, but development in the last few years has not really, has largely stagnated. I don't want to be unpleasant because the Zib people are great friends of ours. The interesting thing about SCIP and Zoplex is they were developed for research. And it's really thanks to a lot of extremely talented researchers that these codes are actually of high performance. But performance wasn't the first aim. And finally, you've got Highs, which was developed mainly at the University of Edinburgh. We solve LP, QP, and MIP, and we have the best benchmark figures for MIP in open source. And Highs was developed for performance, where we don't need to produce research because in the UK, if research has led to impact, it's well worth it for the school. So therefore, we are supported in all ways by the school because we create impact. So why do we need open source solvers? Well, they are needed by those who can't afford commercial software, and these are 3 relatively impoverished groups that might want to do optimization but can't afford commercial software. But it's also needed by those who can afford commercial software. First of all, as people are starting to realize, open source can be good enough, so why pay for a commercial license? Some people are wanting to solve lots and lots of concurrent problems with slightly different data because they're doing a kind of Monte Carlo type approach to the stuff that's uncertain. And they can do that with as many runs of Highs concurrently as they like, but they would need multiple licenses to do it with commercial software. Sometimes the deployment of licensed software is tricky, and also some people some niche areas have concerns over transparency, and of course, being open source, it's all there for you to see. The challenges for open source are principally benchmark performance. The best open source solvers can be at least 10 times slower than Gurobi and the other good commercial solvers, and as a consequence, can't solve some large problems that can be solved with commercial software. And the evidence for that is in the OET and Mittelman benchmarks. The other challenge is funding, and I can only really talk about highs. We are fortunate at the moment. We have got good funding from Breakthrough Energy, which partly funds me and Yvette Galabova, who does our software engineering. It also partly funds our LP and QP solver developer and also our MIP developer. But I've got 3 PhD students who are all industrially funded by Google and MathWorks you've heard of, but Kraken is a UK energy tech company. Can the performance gap be closed? Well, let's look at a bit of context. The commercial solvers that I've mentioned were generally written over decades with large financial resources. The exception is Cardinal, who developed much more rapidly by recruiting developers from other companies and the Zuse Institute, and so really hit the ground running and put a lot of money into it. So they've caught up over 10 years. Each of the high solvers took only about 2 to 4 years to write, so not decades, and it's not been done with large financial resources until recently. Our new LP and QP solver and the multi-threaded MIP solver will help to reduce this performance gap. It's also essential that we retain our developers. I think it's unrealistic to think that the gap can be closed, simply because we will never catch up with the secrets in the commercial codes and the years that have been put into developing them. But I believe that Highs has the best chance of reducing the gap amongst all of the open source codes around, and also I can't conceive of anyone coming up with one that would be better in the short term. For solver benchmarking, well, the Hans Mittelman's benchmarks have been the gold standard for years, and these focus on what we might call numerically clean models that are hard to solve. And they also represent the full range of fields where optimization is required. And so therefore, there's very few energy modeling instances. The OET benchmarking project, the value of this for us is that it's brought solvers and solver developers and modelers together in a sort of systematic way that hasn't happened in the past. It's exposed our solver developers to poorly scaled problems, which is good for us, even if we might actually like modelers to improve the scaling of their problems. And so it's also, I hope, exposed modelers to the value of writing better scaled problems. It also allows changes in solver performance to be monitored. So therefore, the funders like Breakthrough can see the fruits of their investment. And generally, the whole energy modeling ecosystem benefits as a result of OET's benchmarking project. Looking forward, GPU acceleration is a bit of a buzzword. It's encouraging for LP because there are first-order methods. There is a third way of solving LPs by first-order method. And it's available in commercial solvers plus Highs and NVIDIA's QOpt. However, for very clear mathematical reasons, the solution accuracy with these methods can be poor, and it will not be as good as interior point. And that's maths. It's not implementation. There's very limited scope for GPU acceleration in solving MIPS. Essentially, it's the search for feasible solutions that is amenable to some acceleration with GPUs. And the other thing to say is that GPU acceleration for open source comes with a cost in that the best GPUs are very, very expensive, whether you buy them or rent them or whatever. And some of the great results that have been published have only been on the most expensive of GPUs. MIP solver enhancement is coming. Of course, it's ongoing in the commercial solvers. For highs, we've got the multi-threaded MIP solver, which will be out in next month in version 1.15. That is almost a brand new animal in many ways, and Mark is only just starting to see how it behaves. Undoubtedly, we will tune it and learn to tame it over the next 6 months and improve performance quite considerably. We now have the possibility of turning to dedicated features for energy models. Getting the multi-threaded code out really was the first low-hanging fruit in sense for performance. I don't see a lot of sign of progress in other open source solvers, though. In terms of community engagement, we will have continued collaboration with modelers facilitated by the benchmarking project. And we will offer continued encouragement to modelers to improve their scaling. And we also look forward to continued funding to keep this thing moving. Thank you.
Thank you very much, Julian. Since we are slightly ahead of schedule, I can ask the brief clarification questions that were posted in the chat.
Yeah.
To you, Julian. So what about quadratic constraint problems or mixed integer versions of those?
Well, continuous quadratically constrained problems, it's conceivable, not conceivable, it's quite likely that we will extend the interior point solver to handle those. MIQP, that's further off. I think, like a lot of people, we will end up just linearizing and then leveraging the power of our MIP solver rather than trying to do solving QPs at each node.
All right, there's not a question in the chat about scaling, but I think we should probably keep that for the panel discussions because we already had some kind of pre-discussion about scaling. You have an opinion about that. I have a different opinion about it. So let's keep that question. Nicholas, thank you for that question. We'll keep it until the panel discussion at the end, so we can go in more depth. So with that, then we should be giving you some results from our open solver benchmark project, which you've now heard about, but you haven't seen, unless you've gone to our website, you haven't seen results. And we're very happy that we can present these to you today. And my colleague Enrico, who's a senior energy system modeler at OET, is going to kick us off with that. The floor is yours, Enrico.
Thank you, Harry. And yeah, thanks everyone for joining today. Yeah, my name is Enrico, and I'm a senior energy system modeler at yeah, if people in the audience can mute themselves, that would be better. Thanks. And yeah, today we'll present the Open Energy Benchmark and share some of the main findings from our latest assessment of optimization solvers for energy planning models. So energy planning models are becoming larger and more complex every year. We are integrating more technologies, more sectors, higher spatial resolution, longer time horizon, and increasingly detailed representation of uncertainty. And as a result, the optimization problems behind these models often contain millions of variables and constraints. And this makes solver performance a critical bottleneck because if a solver is slow or unable to solve a problem, modelers are often forced to reduce the spatial resolution or a temporal resolution or explore fewer scenarios. And that ultimately affects the robustness of the planning decisions because we cannot fully explore, for example, uncertainties related to technology costs, policies, or climate change. At the same time, open source solvers have improved substantially, as Julian mentioned, in recent years, but it's often difficult to understand where they perform well and where challenges remain. And so this is the main reason why we created the Open Energy Benchmark. So what is it exactly? So the Open Energy Benchmark is an open and automated benchmarking platform built specifically around energy planning applications. And an important point is that the benchmark is intended as an educational and diagnostic resource. So its goal is not to identify a single best solver, because solver performance depends on the problem being solved, the model formulation, the chosen algorithms. And so here in our benchmark, we evaluated 5 solvers, 4 open source, namely CBC, HICE, GLPK, and SCIP, and 1 proprietary solver, Gurobi, which was used as a baseline in the benchmark. And so the benchmark includes 213 problems originating from 13 modeling frameworks, including GenX, Times, PALSA, and many others. And the problems typically range from a few hundred variables to more than 50 million variables. And to make the benchmark reproducible, all runs were performed on standardized cloud infrastructure with fixed time and memory limits. And the results that we show you in the next slides are also fully documented in a report that will be made available on the Open Energy Benchmark website, and also on Zenodo, likely tomorrow or early next week. So stay tuned for that. So now let's look at the results. First, I would like to focus on the type and number of problems that are available in the benchmark set. So 2 figures on the left show the distribution of problems by problem class and size, where for size we mean the number of variables. Panel A shows linear programming problems, whereas panel B shows MLP problems, mixed integer linear programming problems. And we can see that we have more LPs than MLPs. Most of the largest problems in the benchmark are LPs, above 1 million variables, while MLPs tend to be smaller, and also we lack MLP problems with more than 1 million variables. Then on the right, I show 2 figures about the solver success rate, so meaning the percentage of problems that are solved within time and memory limits. And the results again are grouped by problem size, and solvers are identified by different color. So we can see that for smaller problems, most solvers perform reasonably well. However, once LP problems exceed roughly 1 million variables, we observed a sharp decline in success rate for the open source solvers. For MLP, the challenge is even greater, as Julian mentioned, and the addition of discrete decision, in fact, makes these problems significantly harder to solve. And so the main takeaway from this first set of results is that open source solvers work well for many smaller and medium-sized problems, but scalability remains one of the key challenges as models become larger. But the success rate is only part of the story. In fact, even when problems are solved successfully, runtime matters because it determines how many scenarios, for example, can be explored. And so in this slide, I'm showing on the left the average runtime. So again, we have the first panel A showing LP problems, and this panel B, the MLP problems. And on the horizontal axis, I'm showing the number of variables, again, the problem size. And note also that the vertical axis shows the average runtime with a logarithmic scale, so ranging from seconds to hours. And also in this case, lower values are better. And then we have dashed lines indicating the timeout threshold for different problem sizes. We can see that at the smaller scales, again, runtime differences across solvers are relatively minor for LP problems. However, as the problem's scale increases, Gurobi maintains a relatively lower average runtime and solves these larger problems in under an hour. Instead, the open source solvers experience an increase in average runtime approaching the timeout limit for problems with more than 1 million variable. And in the MLP domain, there is a lot of room for improvement for open source solvers, even at the smallest scales. Now, if you look at the two panels on the right, I'm showing the slowdown relative to the fastest solver to better quantify the performance gap that there is among the solvers. So for each problem category, we identified the fastest solver and assigned it a slowdown factor of 1. And all the other bars relative to the other solvers show how many times that solver is slower than the fastest one. So for example, a value of 10 means that the solver took 10 times longer to solve that group of problems. And we can see that depending on the problem class and size, open source solvers can be from a few times up to 2 orders of magnitude slower than the proprietary baseline, for example, in the case of larger MLPs. And overall, among the open source solvers, HICE generally provides the best combination of runtime and success rate. However, it's important to remember that these results reflect default solver configurations. So different algorithm choices and also parameter settings can lead to substantially different outcomes. So the results up to here showed were obtained with the latest version of the solver packages in 2025. But we also wanted to track its progress over different years. And so in the next slide, I'm showing how the solver performance has changed from 2022 to 2025. Here we show the performance change only for 3 solvers, which are the ones with available releases over this period. And the panels on the left column show changes in the fraction of solved problems, and the panels in the right column show changes in the average runtime. And the values shown are relative to the first version that we tracked. And so for success rate, positive change indicates an improvement, whereas for runtime, negative changes indicate faster solution time. And we can see that SCIP, which is in the last row, shows only small changes on this benchmark set. And by contrast, both HICE and Gurobi show measurable improvements in runtime and also to some extent in success rate. But it is important to note that this analysis only included benchmark problems with fewer than 1 million variables and also default solver options. So any performance improvement for larger problems or for specific solver configuration does not show here. But after that, we also wanted to test or see how the solver performance also depend on the algorithms that the solver uses internally. And so to explore this, we perform a complementary analysis to study Hypo, which is a new interior point implementation introduced in HICE. And we compared Hypo against all the existing algorithms available in ICE, which are the simplex method and the previous implementation of the interior point method called IPX. And for reference, we also included the Gurobi results with the full options. And one important note before looking at the results is that both Hypo and IPX runs were configured with the territory feasible solutions, which are not necessarily basic solutions, while Gurobi was evaluated using its default configurations, which always returns a basic solution after crossover. Therefore, the results from IPX, Hypo, and Gurobi should not be interpreted as a direct apples to apples comparison, but I'll leave these details maybe to Julian and Matthias. So this figure specifically show a subset of the entire results that we analyzed and that are available on our website We specifically show in panel A the runtime results for a pipes electricity model for Germany, where we progressively increase the spatial resolution from 2 to 60 nodes on the x-axis. And panel B shows the number of variables resulting from these models that goes from roughly 0.1 or 100, roughly half a million variables to more than 10 million variables. And we can see that the simplex is the first algorithm to hit the timeout threshold at 14 nodes. Then IPX performs better and reach timeout at 20 nodes, whereas Hypo maintains lower runtimes across most of this resolution range and is able to solve instances up to 50 nodes within the 24-hour time limit. So in practical terms, this means that modelers can now solve much larger and more detailed energy planning problems using open source software that was previously possible. And the main takeaway from this study is not the comparison with Gurobi, but rather the significant gains that were achieved through algorithmic innovation in the open source ecosystem. In fact, then if we look at the full results of this additional analysis, Hypo increased the number of LP problems solvable by open source solvers by about 7%, and also solved the models with million variables up to 15 times faster than the previous HICE algorithms. And so looking ahead, first, we see three priorities for our project. First, we are planning a new benchmark campaign at the end of 2026 with additional problems, updated solver version, and also potentially some new or some different non-default solver configurations and more random seeds. Second, we continue to expand the benchmark through community contributions, and we welcome additional benchmark problems from different modeling frameworks and application, and instruction on how to submit new problems are available on the Open Energy benchmark website. And third, we are also exploring governance structures that can support the long-term sustainability of the project while maintaining neutrality, openness, and reproducibility. And if you would like to explore the full results, these are available in our website at the openenergybenchmark.org. And there you can find all the benchmark results and documentation, as well as our Hypo analysis and the open call for benchmark. And you will also find, as I said, tomorrow or early next week, our report on the state of solvers for energy planning. And then you can also access our benchmark code and infrastructure, which is publicly available on GitHub. And if you are interested in contributing in any way, we will be very happy to hear from you. And before closing, I would like to acknowledge the many people and organizations who contributed to this project. So this work was led by Open Energy Transition team with support from Breakthrough Energy. And I would also like to thank all the contributors to this project, including model developers, solver developers, who provided valuable feedback during the past year. Because benchmarking is ultimately a community effort, and the quality and relevance of these results depend on the collaboration between modelers, energy modelers, solver developers, researchers, and also funding organization. And so with that, I would like to thank you for your attention, and I'll be happy to answer any question.
Thank you, Enrico, and very nice results. There are a couple of questions in the chat. I'll just kind of collect them into one for the sake of time. How did you choose which solvers were included? People in the chat are mentioning IP-opt, for instance, other solvers that we could include, or is there a mechanism for people who develop new solvers to have them listed?
We would be happy to include also those, and please reach out to us, and we will make sure to include them in our version 3 of the benchmark, which is expected to run from September to December. So please reach out to us, and there is no barrier to including other solvers.
And of course, you're always welcome to go to GitHub and download the models themselves so you can run them on your own solver. We are particularly interested, of course, in the comparison between open source and commercial solvers. But if, for instance, you're interested in testing another commercial solver that you have a license to, you can just download the benchmark set and test it on your problems as well. Good. Then I think I can call the panel up for the last 25 minutes of this hour. You've already met Julian and you've already met Enrico, but we're also really happy to have Matthias Miltenberger here, who's Manager of Optimization Support at Gurobi. We're really happy that Gurobi is collaborating with us on this particular project and allowing us to do the benchmarking and helping us also come up with a benchmark that helps the ecosystem forward. So happy to have you here, Matthias. And we also have David Paolella, who's Director of Research and Analytics at Breakthrough Energy Grids, who has funded the work that has been presented here. So maybe to kick us off, and also to give the panel members a chance to say a little bit about why they're here, I would like to ask the question first: why is solver benchmarking important to you or to your organization? Why is this something of interest? Maybe starting with Matthias.
Yeah, I'm happy to answer that. Also, thank you for inviting me to this webinar. This is really nice. So why is benchmarking important for me personally as well? I've been doing this for quite a while, even before joining Gurobi, about 6.5 years ago. And so in the open source space, in the SCIP optimization solver suite. But then at Gurobi, I've been basically doing this professionally. And what the goal of the Gurobi experts team is to really help customers to get the most out of the solver. And this often includes parameter tuning or helping people find the best tips and tricks to solve their models in the fastest way possible. And how you do this is really not super easy and requires a lot of experience and patience and also quite a few machines. So I just checked today and we have about 700 compute nodes in our data center that are being used by developers to tune the new parameters or the new developments for the best performance, and also by the experts team and the technical account managers to run very many benchmarks and performance runs for our customers. So that's really quite massive, and this grew a lot over the past years.
All right, thank you. David, do you want to say something about why solver benchmarking is important for your mission?
Sure. Thank you, and appreciate the whole OET team for pulling this together and everyone for attending. I'm on the Breakthrough Energy Grids team, and Breakthrough Energy overall is focused on discovering, developing, and scaling emerging clean technologies to help achieve decarbonization globally, along with clean energy abundance. And my grids team, which was formed about a year ago, is focused on supporting the development of advanced tools and methods for helping energy planners develop the grid globally to achieve a decarbonized future. So, that's pretty broad. I did not come to this work thinking that I would be spending a lot of time with optimization solvers, to be honest. That's something that I think I really learned about early on through that work as a key unlock and also sometimes barrier to achieving that broader mission. And I've had the luck to spend a lot of time learning about that over the last year. So, taking us, I guess, a step back, we are, to achieve our mission, we have identified open source software and tools and data overall as being really important. That's for a number of reasons. So we think that open source tools and data can help make planning faster by improving interoperability, transparency, and trust. We think that open source can make energy modeling more accessible, so broaden the number of people around the world who can use energy models and engage in decision-making processes. And then we think open source tools and data can drive better decisions when it comes to energy planning and grid planning. And we think part of that's related to the ability of open source to drive or foster collaboration and innovation. So bringing more people into the work and thereby developing better tools and methods. So open source solvers, is just one component of that, but a key piece of the puzzle. Ultimately, success for us looks like making it possible to do industry-grade planning studies with as close to a fully open source stack of tools and data as possible. Now, of course, there are many individuals, many companies that won't want to use a full open source stack, and that's fine. We're not necessarily trying to build open source tools and data that can beat commercial tools and data. And I think Julian's right. I mean, it's not realistic to think that HISE or other open solvers can entirely close the gap with commercial solvers. But we do want to reduce the gap. And we think that's important to bringing a lot more people into this work. So super excited to see you guys release these results, and looking forward to some questions from the group.
Yeah, thank you. And also just a reminder, you can type in the chat if you have questions for the panel. But in the meantime, Julian, you've already in your presentation said why the Open Energy Benchmark project was important to you in the HISE work. Can you maybe give us an example of how the benchmark has changed or has helped you develop HISE?
Yeah, there's one specific case where Filippo ran looked at results from HYPO on the energy OET benchmark problems and realized that in a way they're not as hard to solve the way that some of the Mittelman problems are hard to solve. And in fact, it's motivated him to develop a simplified decomposition matrix decomposition algorithm for HYPO, which will get a performance gain on these problems. So yeah, that's there's a lot of focus on really, really hard, modest-sized problems to solve in Mittelman, but solving easy, very large problems is a slightly different, but just as interesting topic.
Thank you. And finally, Enrico, you're also an energy modeler, so you also run energy modelers. Mm-hmm. How does the benchmark help you in your other work at OET as a modeler?
Yeah, so I'll be quick since I already talked a bit during the presentation, but benchmarking help us understand where we are today and what needs to be improved in the solver ecosystem, and also to support the energy transition, and not also on the solver ecosystem, and also how we can, as a modelers, become more familiar and more knowledgeable about solvers, how to define the proper settings in the solvers, which I highly recommend every modelers to get familiar to, because they do make a big difference in your solving time.
Thank you. That's a nice bridge to the question that was asked earlier in the chat by someone, and also a question that we had thought about before. So energy modelers are typically not OR specialists. I'm an economist. I somehow got into energy modeling. We have colleagues who have a wide range of backgrounds and that somehow got into energy modeling. So they want to define a problem in the software of their choice, hand it over to a solver, and just not bother with having to do any complicated maths. from a solver perspective, I've talked to many solver developers, and they always tell me these problems are horrid, very badly scaled. Why are you handing these problems to a solver? Why are you not, improving the quality of your model first before you're doing that? How do we deal with this? How can we get these communities closer together? Should open source solvers, follow the same direction that also proprietary solvers have gone into, and just make it as easy as possible for the users? Do all the pre-processing for them, or Julian, you've mentioned we should educate the engineers on how they need to scale models. Maybe Julian, do you want to give a first reaction?
Yeah, I think one thing that's perhaps not appreciated by practitioners is that if you scale your models well, then generally the solver will solve them faster. And although code like Gurobi has got techniques, so I believe, obviously we can't see inside, which will mitigate some bad scaling by users, ultimately, if you're giving us a badly scaled problem and telling us to solve it to these tolerances, then in a way that's what we are obliged to try and do, and it may just take an awful lot longer. Even if you try and scale the problem internally, you may and therefore make it easier for you to solve, and we consider doing this. Ultimately, you may not be then solving the original problem to the tolerances that are requested by the user. So I think that's still quite an important thing to try and get over. I mean, to users.
Yeah. May I add something?
Yeah, go ahead.
So actually, this badly scaled models are also one of the the greatest issues that we fight with in helping customers with their models when they send them to us for performance tuning, and we have to tell them, well, yes, we can conduct performance tuning here, parameter tuning, but also you need to work on your model because there is just so much numerical dirt in there, or it's just unclear what this model is supposed to represent. Maybe those tolerances don't even mean much in regard to your to the range of your variables. So you always need to make sure that your coefficients and your numbers are as close together as possible, as close to one as possible. So you would want to avoid these huge ranges, for instance, in the right-hand side, in the matrix coefficients, and also in the objective coefficient. So we'd like to have this as close together as possible. And then you can also expect fewer numerical issues. And yes, as Julian said, just scaling them is usually not going to solve the problem, because then in the end you're solving a nicer problem. But if you then scale the solution back into your original space, you also scale up all those violations, and that used to be within your tolerances, but then they may not be tolerable anymore.
Got a nice example actually, which I think really rams the message home. I had a model sent to me, and it couldn't be solved by Gurobi, it couldn't be solved by SCIP, and it couldn't be solved by Highs. It was actually solvable by LP-Sol. And I looked at it, and all of the non-zero bounds were of order 10 to the 9, because this was an energy engineer modeling something in watts that was really gigawatts and wanting a tolerance which was something like microwatts. And that's complete scientific nonsense. And as soon as I scaled all of the bounds down by 10 to the 9, the problem solved very easily with Highs. And it was trivial to solve then. But you're basically running out of machine precision to solve that problem to those tolerances.
Yeah, so maybe the open energy benchmark also needs a section on how to use solvers for modelers. Maybe that's something to add for the future. Can I ask a different question? Because we've already heard the term parameters and solver tuning. Enrico, you mentioned several times in your presentation, these are just the default settings. Mm-hmm. In your experience, what does that mean? What kind of benefits have you seen if you do change some of these parameters?
Yeah, so typically modeler uses these tools like as an out-of-the-box tool. So because it takes some learning to understand all the different solver options, and it takes time. So sometimes modeler rely on these default options, and that can be it's not a very nice thing to do, because as we show with these analysis of selecting different algorithms from the same solver, that could improve things quite a lot. And I was aware that Gurobi has many solver options so that you can select to relax some conditions that would allow you to increase or reduce the runtime of your runs. So I would say that I recommend everyone to get familiar with this solver option in advance of running like very complex energy system models.
And what is the panel thing? What does this mean for benchmarking? Because it means that if I hear correctly, Enrico, that many of the problems could be solved faster than the time that's indicated in the benchmark if the solver was tailored to that specific problem. Matthias, do you have an opinion about what's a fair way to benchmark in this setting?
It's really, really hard to say. I don't think it's fair to use custom parameters, because then you would have to, like, you can only use a very small set of problems and conduct some performance tuning on those, parameter tuning, do this for all the solvers, and then kind of say, okay, this is probably close to the best possible times for all those different solvers. But this takes a lot of computational time to do, and I guess we can't do this for the whole benchmark set. Maybe just to give us a reference, so when we in the experts team, when we get customer models, we also try to reduce this to a set of 3 to 5 models that we actually tune. So when they send us 100 models, we're not going to tell them, okay, we're going to tune all of those, but we try to reduce this to a representative set, because it's just not computationally feasible otherwise. And then ideally, the solver should just choose the best parameters internally, automatically. And yes, I also see and know that this is an unfair advantage for the commercial solvers, because they just have more resources to make that tuning internally that the open source community just does not have.
Yes, I think that kind of cues me in to say that in those original LP results, for example, that Enrico presented, they were with the Highs simplex solver, because by default Highs uses simplex to solve an LP. Expert users will choose our interior point algorithm if they know their problem is large, but that's our out-of-the-box default. And we're just not yet at the stage, it'll come fairly soon, where we look at the problem parameters of an LP and decide internally which of our 3 or 4 LP solvers are actually going to be used on this problem. And so it'll come for us, and then suddenly you'll see a vast improvement in the performance of Highs on the OET benchmarks, because it's using interior point most of the time, unless the problems are small, in which case it'll use, well, maybe the other interior point solver or simplex. So yeah, but I certainly agree that tuning, it's tuning the solvers, allowing them to be tuned for the benchmarks, is you're opening a horrible can of worms.
Yeah.
Right. Thank you. Can I ask a different question and start with you, David? So this benchmark website started as a project, but we're increasingly seeing this being a shared resource for modelers, for solver developers. What role do you think this could play in the ecosystem going forward, and perhaps also what does it mean for its governance?
Yeah, it's a good question, and I'll just start by saying I think you guys have already achieved so much with this. So obviously there's a lot of directions to go in, I think, but major kudos to the whole team for everything you've already achieved. I mean, so I think we've already hit on a number of directions that this could go in and be very valuable. I mean, obviously, it's already helping solver developers. identify ways to improve their tools. That's great. We should keep pushing on that. I think the idea of helping model tool developers figure out how to better to optimize their tools and make them more efficient at interfacing with solvers, that I think seems like something that's worth putting a lot more effort into. And then I think the point on helping to educate modelers about how to sort of weigh the costs and benefits of different levels of granularity in their problem design seems like a very useful thing. It seems like there's a lot more juice that can be squeezed out of the existing tools that we have, but people don't know how to use them efficiently and use them sort of in the right ways for the problems that they're working on. And I mean, that's just probably a result of a lot of people who are trying to do energy planning who are not mathematicians. And so figuring out how to better engage with those groups, I think, is really important. That's a little bit broader than governance, but I think that's about how do we build more partnership and collaboration and engagement with this work. So I don't necessarily have answers, but I do think that should be the goal. As for governance, I think you guys are already doing this out in the open, so transparency in how you're developing and operating this platform is key. I think the more that we can also get other institutions or organizations as core partners, both in the governance and development, would be quite valuable. I'd be very curious to hear from the rest of the panel and really offline from anyone who's on the call if they have ideas on how to expand involvement.
Anyone else on the panel who wants to respond to this?
So I would add on that, yes, or like, yeah, basically say the same, that also just modelers who are not so much interested in on the solver side still need to have some kind of understanding of the solver component. Because if not, they may just think their current model, they just put it into one solver. They say, oh no, it's too slow, it can't be solved. And then they are disappointed and give up. Whereas maybe just finding a different formulation would have just solved it. Finding a different solver or finding a different solver parameter might have solved it. So this would be a bad case of giving up on the idea of optimization or of this kind of model. And yeah, it might have been salvageable by some a bit deeper understanding. And I think those transparent benchmarks can probably help to get a better feeling for what is possible.
Julian, do you want to respond?
Other than to saying that decent scaling of problems it's not rocket science, it's not high-powered mathematics. It's simply any decision variable that's not zero, you should have its value to be approximately 1 of that order, not 10 to the 6 and not 10 to the minus 3 if you wanted to solve well. So just simply scaling, getting the units right, thinking about units and using sensible units. Obviously, that example I gave was totally not sensible units for the problem. And so it's you don't need to know a lot of maths. It's an engineering problem. It's not a maths problem.
Thank you, Enrico. I think we'll leave the final word to you. What can we expect? You've already said a little bit about what we can expect from this solver benchmark, but do you have any final words about how people can contribute or how people can help us, build this community even further?
Yeah, for contributing, I would welcome. We would welcome more problems that could be added to our benchmark set for the next benchmark run. But I would also add that given the conversation of today and some of the conversations that we had in the past weeks, this benchmark platform could also become like an educational resources mainly for modelers to understand which is the current landscape of solvers, how solver settings can influence your results, and also these issues about problem scaling that are also very relevant in our field. So I believe that our platform and our project could better communicate this, and we'll try to make sure to address it also in the coming months.
Thank you very much. And yes, in the chat, people are saying what I also had in mind is maybe we need to do a workshop, a practical hands-on workshop on model scaling for engineers and economists. We'll think about that and get back to you. But for now, we are at our time. Thank you very much to our panel members. Thank you to Julian and to Enrico for their talks. Keep in touch. Have a look at our website. Let us know what you think, and we'll see you next time.